Hello everybody, welcome back to our Math A&A Friday. In previous week, we talked about introduce complex number. Now we talk more of different forms of the complex number. Next week, we will talk about how to work with it, find the nth root of the complex number. It's very complicated for next week's stuff, so today's is a great foundation for it, so concentrate. Okay, let's start. It is additional higher level. Okay, number and algebra, we still on that AHL. Now we will on 1.10. Wow, 10 section already, okay, or 10 units, you can say. It's a more forms of a complex number. Before we have Cartesian form, right now we have a modulus argument form. In other words, it is a Cartesian coordinates, polar coordinates complex form. Okay, complex number follow the polar coordinates and work on. Becomes like this. Okay, so the form is z equal r 6 theta and modulus is r, argument is theta, but what are they? It is a concept, but remember we can have eigenplane. Okay, eigenplane, the horizontal axis is the real part of the complex number, vertical axis is the imaginary part of the complex number. You can plot the point of the complex number here. A(xy) means the complex number z equals x plus yi. X is the real part and the yi is the imaginary part, and it will be like this. Okay, now we change the Cartesian coordinate into a polar coordinate. Do you remember polar coordinate is measured from the positive axis in the anti-clockwise direction, so this theta. And polar coordinates also measure the distance of the point from the center R. In our terminology, in complex number, but theta is an angle, and then argument, and R is the modulus, the length. Okay, so we have the polar form. Okay, R as z equals, and then by this polar form R and theta. If we have R and theta, how to find x and y? X is easy. X is the adjacent side, right? So it's equal to R cosine theta. And y is the opposite side, so it equals to r sine theta. So x plus iy becomes r cosine theta plus r sine theta I. Take out the r, so it becomes r cosine theta plus I sine theta. Just a definition of changing the Cartesian coordinate to polar coordinates in the eigenplane. So always a cosine theta plus I sine theta, always cosine plus I sine, so we take it out as cis. Okay. CIS is cosine plus I sine, CIS, okay? And the argument is theta is the argument of this complex number set, okay? It is defined. Defined is rigorous, okay? From the positive x-axis in the anti-clockwise direction. Okay? And how to find it? Theta is the arctangent of y over x is the arctangent of an imaginary part over the real part. Okay? And modulus is easy to find. It's just square root x squared plus y squared. But by this modulus argument form, what is the complex conjugate? Complex conjugate says ours is negative theta. Negative theta. And why we love this form so much? Because it can be rotated easily. Okay, imagine this point rotated by angle theta 1 in the anti-clockwise direction. Just theta increased by theta 1 becomes theta plus theta 1. So the new complex number can be found easily for rotation by this modulus arguments form. Okay, get some second on this page and we'll work on our example. Test. Okay, use the binomial theorem to expand this 6 theta cube. Hence, find the imaginary parts of a 6 theta cube. Okay, nothing. It means 1. Okay, R is 1. Okay, try to expand it. Cosine theta plus I sine theta cubic. Expand it. What's that? Do you remember binomial theorem? Coefficient is cubic 1 Okay, try. Yes, you got it. Okay, just expand them and then get all the get 1 cosine cube theta, cosine square theta, I sine theta, cosine theta, I sine theta all square, I sine theta cube. And then group the real part and imaginary part together. The first is real, second is imaginary, third is real, fourth is imaginary. So we have the imaginary parts of it to be v cosine square theta sine theta minus sine cube theta. We'll use it later. Actually, this is sine theta. Very funny. And then how to find the polar coordinates? R has no problem. The problem is on the argument theta. So what you need to do is to mark the set on the eigenplane, and then you load this feeder. First of all, find the angle phi first. It's the absolute y over x inverse tangent. Okay, and then theta must be smaller than 90 degrees. And then plot the point on the eigenplane, and from the thing on the plane, you notice how to find theta. Maybe theta is 180 degree minus 5, or maybe 90 degree plus 5, or whatever. Okay, you find out quickly. Okay, transform complex number 4 minus 5r into polar form. It means r 6 theta. So what is r? What is the modulus? What is theta? What is the argument? Okay, pause and work on it. Welcome back. That's it. Okay, z squared plus 5 squared square root 6.40 is the modulus, and the angle is minus 5 over 6 absolute, and then 51.3 degree. But where is it? It is a positive x-axis and negative y-axis, so it should be here, and it should be a big angle from 0, 180, 360 minus theta. So it's 360 degree minus 51.3 is the argument of the complex number. 309. You got it? Well done. You can change it to anything. 3 plus 6i, 1 minus 1 plus 2i, anything you can do to get some exercise for yourself. Okay. And the other thing is called Euler form. Remember, we have a Cartesian form, we have polar form, and then now it's an Euler form. Euler form is z equals r e I theta. Fairly similar, but now the theta has to be expressed in the unit of radian, not degree. In 1748, wow, nearly 300 years ago, Euler first used e to represent a complex number, Euler number. Euler form is like this way. Cosine theta plus sine theta equals 6 EI theta. Definition. So theta has to be expressed in the units of radian. Very easy. A round circle with 360 degrees is 2 pi r about the circumference. Okay. 180 degrees is pi. 90 degrees is pi over 2. 45 degrees is pi over 4. Actually, the equation is theta in radian equals theta in degree multiplied by pi radian over 180 degree. Okay. So remember, the original angle of degree has to be divided by 180, right? And it has to be multiplied by pi. Right? So the complex conjugate of a set is z bar. Z bar is r e I theta. Okay, try to work on it. Okay, bring out your calculator and find this the result set in Euler form. Welcome back. Okay, what do you get? Everyone is harder. Set. Do all the thing, and then minus 7 plus 7i. Oh, good. So it is in the fourth quadrant. Okay, in the second quadrant. So it should be pi minus the angle. What's the angle? Okay, absolute. 7 over negative 7 is a pi. It means pi over 4. So it should be pi minus pi over 4. So this is 3 pi over 4 in this form. Got it? Well done. So why we need a different form? Why we have Cartesian form, polar form, Euler form? Because they are good at different usage. Okay. For the Euler form is a little bit complicated. We need to change the angle to radian. Okay. For polar form or Cartesian, there's no need to change the unit yet. Okay. So the difference, the sum and difference is the Cartesian form is like this, right? Plus or minus 7. And the product and quotient Cartesian form or to Euler form. Okay. Yeah. So you got all the thing, multiply them or divide them or whatever. This is the thing. Okay, challenge. Okay, try to work on it. Euler form. So remember Euler form. So R1 over R2, and then EI theta 2 equals theta 1 equals minus theta 2. Okay, that's it. So you find out theta 1, theta 2, but remember in radian. Try. Welcome back. It's not that hard, right? You work on it. You learn. So Z1 is here, 5. Z2 is 2 square root m. And then divide them. So the first argument minus the last one. And then this like it. You got it? Of course, you realize you can have a fee to say for you got 0.791. You can. So thank you. Very short chapter, but very important. Introduce the polar form and introduce the Euler form. We'll use them very frequently, even more than the Cartesian form. Okay. So thank you for your support. Okay, being with us. Okay, if you like our sharing, like, subscribe, and share it with your friends. Okay. See you next Friday. Bye bye.